Okay, so now we are learning about direction fields and Euler's method. Okay, and yeah, let me highlight this. This is an important paragraph here. Hold on. I'm sorry I cut the guy's head off, but let me see here. Is this going to show? Wait, hold on. Is this? Oh, okay, here we are. Okay, so they mentioned right in the beginning of section 7.2 that unfortunately it's impossible to solve most differential equations in the sense of obtaining an explicit formula for the solution. Although I will say many important differential equations you can solve. But, you know, what the author's saying is true. In this section, we show that despite the absence of an explicit solution, we can still learn a lot about the solution through a graphical approach. Now, a graphical approach would involve direction fields, and a numerical approach would involve what's called Euler's method. Okay, so let's go ahead here to the example that they work with, because it's a pretty good example. And okay, so I have some things highlighted here. Okay, but maybe just to make it a little more dynamic, I'll unhighlight it and then highlight it. Okay, sorry class, let me just get this. Thank you. Okay, so this here is a differential equation. dy dx is equal to x plus y. So the derivative of y with respect to x, it depends on x and y. And we're told that the initial condition is y of 0 equals 1. That means when x equals 0, y equals 1. So whatever the solution is to this differential equation, it has to pass through the point 0, 1. So we don't know a formula for the solution, right? We don't have a formula for the solution. So how can we possibly sketch a graph for the solution? Well, what do we have? We have the differential equation. And that differential equation is tremendously valuable because the equation y prime equals x plus y tells us that the slope of any point, any xy coordinate on the graph, would be equal to the sum of the x and y coordinates of the point. Okay, so it's easy to see this in a figure. So let's look at a figure here. Okay, figure 1. Okay, so what they've done is they've picked 2 points, one in the first quadrant, the x2, y2, and another point in the second quadrant, x1, y1. And what they've done is they've like, let's focus on the point x2, y2. It's in the first quadrant, and they're saying that the slope of the tangent line, or tangent line to the solution at the point x2, y2 has to be positive. Has to be positive. Now, why would that be? Why would that be? Well, we'll come back to the picture, but let's look at the differential equation. Y prime equals x plus y, and we're told that y of 0 equals 1. Okay, and certainly I can recreate a little bit of the figure, figure 1. Okay, why aren't you drawing? Draw, thank you. So figure 1, they have, and I'm looking at it here. You know, they have this point, x2, y2. And they just draw what the solution looks like. Don't worry about that right now, but the solution looks like this. Okay, so if the solution passes through, and incidentally, oh, hold on. What's this point here? What are the coordinates for that point?
0, 1.
0, 1.
That's right. Very good, because this is your y of x. This is your solution to the differential equation. And that's right. The solution passes through 0, 1 because of the initial condition. But also, they're saying that at the point x2, y2, which is in the first quadrant, okay, the tangent line is positive. So right here, they're drawing a tangent line with positive slope. How do we know? Why should the tangent line have a positive slope? Why doesn't it have a negative slope? Look at the differential equation. We're in quadrant 1.
Both the x2, y2 is positive.
That's right. Good, Leping. In the first quadrant, the x2, y2, the x and y coordinates are positive. So if you add x and y, which is what the differential equation says to do, add the x coordinate and the y coordinate, that will equal your derivative. Well, the x2 plus y2, okay, x2 plus y2 is greater than 0. And so that means your derivative is greater than 0 at x2, y2. In other words, at x2, y2, y prime, which is x2 plus y2, has to be positive. And therefore, that's the reason why the tangent line has a positive slope. Are there any questions on that? All right, let me ask you this. What's the slope of this tangent line? Try to draw it the best I can. The tangent line that passes through the point 0, 1. What slope does it have? And 1, that's right. And why is that, Leping?
It's because it passed 0, 1 point. So 0 plus 1 is 1.
That's exactly right. 0 plus 1 is 1. That's right. Good. Let's draw another tangent line maybe over here. Just give me a moment here. Yeah. Maybe like right here. So okay, through the point x1, y1, they're saying, well, the slope is negative. So they're saying at x1, y1, y prime, which is equal to x1 plus y1, would have, the derivative would be negative. Hence, the tangent line has a negative slope. Why would that be?
Because you're in quadrant 2.
That's right, we're in quadrant 2. But couldn't I have, and in quadrant 2, x coordinates are negative, y coordinates are positive, but couldn't I get a slope that has, or couldn't I find a point where the sum of the x and y coordinates is positive? Why for this point, x1, y1, is the slope negative there for that tangent line? I'm not sure. I mean, it's an intuitive thing. Okay, Samuel, that's what I was hoping to hear. Very good. It's farther along the x-axis. This coordinate here, right here, the x-coordinate is like, in terms of like the x and y coordinates, the x is negative, the y is positive, but the magnitude of x is more. It's more negative. The x is more negative than the y coordinate is positive. So good. And let me see, there was another chat thing. X will always be more negative than y is positive. That's right, Samuel. So you see, based on, you know, all we've done, we're creating what's called a direction field here. The solution, whatever it is, has to obey the direction field. It has to obey the tangents, the tangent lines, and the tangent lines serve as a guide to tell you what the solution looks like. So if we go now back to the book, we go back to the book here. Okay, here in figure 3, they give an entire direction field for this differential equation. What they've done is they've picked points, different points in the different quadrants, and based on the values of the x and y coordinates, they draw the tangent lines, and from there you can get an idea of what the direction field looks like. Now, at the level we're at in Calculus 2, we're learning the fundamentals, and so the slope fields are going to be, that you look at, or I'm sorry, direction fields that you look at, they're going to be pretty simple. But when you get in like differential equations, the direction fields you'll look at, you'll have computer software, MATLAB, to help you generate the direction fields. Okay, but for our purposes, pretty much you're going to be looking at pictures of direction fields and trying to match the direction field with a differential equation so that you can learn about direction fields. Okay, now let me show you something else here in the figure. So in figure 4, they're drawing a solution curve through the point 0, 1 and obeying the differential equation y prime equals x plus y. So in other words, remember the the initial value problem that they start with in the book, okay, this initial value problem has a solution. The solution passes through the point 0, 1, and the solution has to obey the differential equation. What does that solution look like? That solution looks like this solution here. Okay? You see how the red solution obeys follows the direction field? That's why it's called a direction field. It doesn't fight. It's like, think of it like current, like water current. And the solution follows the current. And if you were to pick another point in the direction field, the solution would look differently. The solutions don't normally, for well-behaved differential equations, the solutions aren't going to overlap. Okay, are there any questions on that? Okay, now let me ask you a question. Along the line y equals negative x, so I know that you know what y equals x looks like. I know you know that line passes through the origin and has a positive slope of 1. The line y equals negative x will pass through the origin, and it'll have a slope of negative 1. Along the line y equals negative 1, if we were to superimpose that line, or just don't superimpose it because it's a direction field, but imagine the line y equals negative x. What can you tell me about the slopes along that line? That line, imaginary line, for this direction field in figure 4. What can you tell me about the tangents? The little tangent lines. For y equals negative x. That's correct, Samuel. It goes through. So what I mean is, well, let me phrase it another way. Hold on. Let me go to the whiteboard. So, well, hold that thought, Nathan. Hold that thought. So here's our differential equation, y prime equals x plus y. Let's not worry about an initial condition. So when y is equal to negative x, okay, when y equals negative x, what does y prime equal? When y equals negative x.
0.
In other words, that's right. Good. Good. So what I'm saying is, well, hold on. I should have used my little line here. Okay, so there's a x-axis, y-axis, and I'll draw the line. There's the line, y equals negative x. So if y equals negative x, y prime is going to equal x plus, hold on, y prime is going to equal x plus what? What's going to go here?
Negative 1.
Well, here's the differential equation. And I want to know if I demand that my xy coordinates all lie on the line, y equals negative x. Y prime then would equal x plus y. But what is y equal to?
Oh, negative x.
That's right. Along this line, y equals negative x. And so y prime then will equal 0, as the Ping pointed out. So can anybody draw in what the tangent lines are going to look like along this line y equals negative x?
They're just going to be straight line segments.
Straight lines, okay. Vertical or horizontal, Samuel?
Neither, diagonal.
Are they going to look like this?
No, they're going to be diagonal.
Well, but if y prime equals 0, if y prime equals 0, what lines have slope of 0? What kind of lines?
Horizontal line.
Horizontal lines, right? Horizontal lines have a slope of 0. And so in the direction field along the line y equals negative x, this is what the tangent lines should look like. Okay. All right. So if we go back to the picture, the textbook, and this is all in the recording. You see there, and I appreciate all participation. You're learning. You know, students aren't always going to say the right answer. That's okay. You're learning. Here. Do you see there in the direction field how along the line y equals negative x, the tangents look flat? You see that? You have to let me know if you're comfortable with that. See, direction fields, if you look at certain parts of the direction field, you'll see interesting behavior. And usually that behavior can be explained, just like I explained here. But so what I'm saying is in figure 4, this is the direction field, complete direction field for y prime equals x plus y. Along the line y equals negative x, the tangent lines are horizontal. Do you see that in the direction field? Maybe give me a thumbs up if you're seeing that. Sean sees that. And Nicole. Okay, and Leping. All right, good, good. Yeah, is anybody not seeing that or uncomfortable with that? Samuel?
Yeah, I'm not understanding what you see there.
Okay, hang on. Let me go back to the whiteboard here. I wish I could save my whiteboard, but let me just, chances are a few other folks have the same kind of question. So this is very important. So here's x-axis, y-axis. And gosh darn it. Okay, there's the line y equals negative x, right?
Right.
Okay. Now, our differential equation is y prime equals x plus y.
Yeah.
And I notice in the direction field, okay, I notice in the direction field that along this line, y equals negative x. I mean, if you look at figure 4, look at figure 4 in your ebook, okay, from section 7.2, all the slopes here are horizontal. Okay, and there's a lot of other slopes in the direction field, a lot of other activity going on. Okay, but along that line, y equals negative x, all the slopes are flat. Why is that? Why is that? Well, if y equals negative x, then that means that y prime just, so y prime is always equal to x plus y, x plus y. But now I'm studying coordinates that are on the line y equals negative x. When y equals negative x, y prime is going to equal x, right? Plus, right? Negative x. Because what is y? Y equals negative x. So that means x plus negative x is 0, y prime equals 0. So anywhere along this y equals negative x line, the tangents have to be flat because the derivative equals 0.
Right, I get
for
that.
any point. So now we're drawing the tangents. We're creating. This is why in the direction field, all of these tangents are flat because they all have slope 0. Does that help you feel a little better?
Yeah, so I understand it with y prime equals 0, but I'm just having trouble understanding it with our current our current problem.
I'll tell you what, I have an idea. I'm actually glad you asked that question because in this example here, one moment here. If I can get it to show. I have a little exercise. Okay, I have a little exercise. Can everybody see the 4 direction fields? Good. Good, excellent. So you have 4 differential equations. And what you want to do is, and then you have 4 direction fields below. What you want to do is you want to match the direction field, the differential equation with the correct direction field. So like for instance in A, okay, what would be an interesting value for y in A? 2. Good. Y equals 2. Now when y equals 2, what's y prime equal to? It equals 0. Right? That's right, Nicole. So that means along the line, the horizontal line, y equals 2, if a direction field is a direction field for this first differential equation, then along the line y equals 2, that horizontal line, slopes have to be what? They have to equal 0. They have to be flat. So look at the four direction fields below. Which direction fields along the line y equals 2 are the slopes flat? The first graph, okay. I think I'm seeing that.
The third
And
one too.
which one, Maria?
The third one.
The third one, okay. I agree. I agree. So let's see. So you see here, here's the line y equals 2. Got to get it just right. Man, that's kind of picky, isn't it? Okay. By the way, what's the problem? What's the problem with graph 4 along the line y equals 2? Why doesn't that work? Are the slopes flat along the line y equals 2 in graph 4? Yeah, slopes are changing. That's right, Renat. So that means that for this first differential equation, the choices are either going to be 1 or 3. Well, there's only one right choice. Okay, so what you have to do now, what's another differential equation that maybe might be a good one to look at now? Look at B. Direction fields are just the slopes. That's right. Okay, so so what I want you to do is I want you to try to match the direction fields to the differential equations. Okay, I've given you some guidance to get you started, but I don't want to give you too much guidance, or I'll be taking the fun away, right? How many think this is going to be kind of a fun problem? You're going to actually take about 5 minutes now to do that. Match the differential equation with its direction field. Okay, I don't want to take all the fun away. So take a few moments and see what answers you get, and then I'll check with you. So about 5 minutes here, and then we'll go over the answers. Okay, so let's see here. What do you think the answer is for A? Okay, I'm hearing 3. Okay. What about B? 1. Okay. Okay. C. Okay. Maybe 4. Okay. Okay. All right. And then by process of elimination, D would have to be choice 2. Okay. Well, let me see here, actually. That sounds right. Let's see if we can, and you can zoom if you need to on the right. So y prime equals 2y. Along the line y equals 2, the slopes are flat. So we were down to choices 1 and 3. But for choice B, slopes are flat when y equals 2, and what else? When else are slopes flat for choice B?
X equals 0.
That's right. That's right, Leping. That's right, Samuel. So it would mean then that, let's see here. Hold on here, one moment. Yeah, for B, it would be choice 1. So B would have to be choice 1, because in choice 1, you have flat slopes along the line y equals 2, but also along the line x equals 0. And that's not the case for 3. So very good. That means then that for A has to be choice 3, B has to be choice 1. Okay. Now, what about here for C? For C, okay, for C, let's see here. When is y prime equal to 0? Well, it equals 0 when x plus y minus 1 equals 0, right? That means it'll equal 0. So C, the differential equation, will equal 0 when y equals negative x plus 1, right? When y equals negative x plus 1. So you're saying that has to be choice 4. And that's right, because if you look along the line y equals negative x plus 1, that's going to be this line here. It's a line that has a slope of negative 1, but has a y-intercept of 1. The slopes are all flat along that line. Very good, very good. Are there any questions on this kind of idea? Okay, all right. Well, let us then go back into the ebook. Now, we talked about direction fields. Now we want to talk about a method called Euler's method. Okay, a method called Euler's method. We want to be able to find values of the solution, or at least approximate the values of the solution. And that procedure is what's called Euler's method. Okay, so I think actually I'm going to go to figure 15 in the ebook. Let me find it here. Yeah, one moment. One moment. Yeah. Okay, this will work. Let me go there, actually. Share application. Okay. So, all right. If we want to approximate values to a solution of a differential equation, Euler's method says start at some initial value. So the initial value here is the point x sub 0, y sub 0 in figure 15. That's like your initial value. And since the solution must pass through that point, we know that point is on our solution. But we want to estimate another point on the solution a little bit further away from x sub 0. So if we were to try to estimate the point x sub 1, y sub 1, or no, let me say it this way. If we wanted to estimate our solution if we want to estimate our solution to the differential equation when the value of x is x1, what would y1 equal? Well, what we can do is we can use the point x sub 0, y sub 0 to, I mean, we can compute the derivative at that point. And the derivative is the slope of the tangent line at the point x sub 0, y sub 0. So you see there, they draw the blue tangent line out a distance h away from the initial point x sub 0 out to x1. And the value of that tangent line when at x1 would be y1. That y1 would be an approximation to the solution, the red solution there. Now it's off a bit, right? Because we're moving away from the initial point. But that's the idea. That's the idea behind the Euler's method. Sometimes people call it stepping along the tangent lines. You see, if you have an initial point, you can get a tangent line. And then if you pick a point on the tangent line, you can find another tangent line because you know the value of the derivative based on the differential equation. So essentially what happens is, like if you had Euler's method approximation for a solution curve, and you were to go out two step sizes of a half, the tip of the green line segment would be when x equals 1. The tip of that green line segment would be the approximation to the solution. But of course, at x equals 1, the value of the green line segment is pretty far, well, it's not very good. It doesn't approximate the red solution well at all, right? So if you pick smaller step sizes, like a step size of 0.14, like they do here in figure 14, you see the tangent lines approximate the solution curve better. So the smaller your step size is, the better you approximate the solution curve. So in a nutshell, the algorithm for Euler's method is this. Okay, if we do iterative computations, the y1 is equal to y sub 0 plus some step size h times big F of x sub 0, y sub 0. Now, big F of x sub 0, y sub 0 stands for the derivative of, it's the derivative of y at the point x sub 0, y sub 0. That's what that big F function means. And then y sub 2, let me just hold on here. Let me maybe, let me make sure. Yeah, so this is y sub 1. Now y sub 2 is going to take the approximations you got from your first iteration, and in other words, you estimate y2 based off of the information you got from on previously. You know what the y1 approximation is, and you know what x1 is and y1. And you can keep iterating, and we'll look at an example of this. We'll look at an example, but you can keep iterating, okay? And you're going to be doing you're going to be working this out by hand. So you're going to have very simple examples to work with, very simple examples. But this is the final algorithm for Euler's method. Hold on, let me just, and then I'll do an example with you here. Hold on, I don't want that blue to show. Let's get the blue off. I don't know why the blue's there. Okay, there we go. Euler's method says you can approximate values for the solution of an initial value problem using step size h, using this algorithm. But what you need is a concrete example. So let me show you a concrete example here. I should have it here. Yeah. Okay, take a moment to copy this example down. And this will be our final example for today. I will get the homework posted for chapter 7 for sections 7.1 and 7.2. But right now you're concerned about getting ready for the exam. But certainly by I think by hopefully Saturday at noon, I can have the new assignments posted for you. Yes, Nicole, the homework for section 7.1 and 7.2. No, it won't be. Well, the homework for section 7.1 and 7.2 would be due a week from today. A week from today. Okay. Okay. You're welcome. TYSM, thank you so much. Hey, I'm starting to learn. I'm starting to kind of learn this stuff. Okay, these abbreviations. I didn't grow up with this, you know, but I'm getting better. I'm getting better. When I was your age, you know, Pac-Man was the big thing. You know, when I was a teenager, how many have heard of Pac-Man? Okay, Marcus says that was like, you know, wow, let's go play Pac-Man, you know. But now I think people are playing like Fortnite. Has anybody heard of Fortnite and some of these other games? Okay, Tal's heard of it, and Sean. Okay, all right. Nicole, you know. All right. Unfortunately, yes. Okay. All right, Samuel. All right, let me give you a moment to copy it down. Okay, so we want to use Euler's method with step size of 1/2 to estimate y, the solution when x equals 3. That's what y of 3 is. We want to estimate the solution for this initial value problem. Okay, so we're going to use Euler's method. Hold on here. Let me just get this off here. One moment. Okay, that's fine. So we want to use Euler's method with step size at 1/2, 0.5, to estimate y of 3 for the solution of this initial value problem. Now, what I'm going to do right off the bat here is I'm going to draw a little line here, line segment, and I'm going to put in some values. Okay. I have to use the okay. This is x here. Now we're starting at x equals 1, right? Because we're told that y of 1 equals 0. So that means this is our starting value of x equals 1. We want to estimate what the solution is when x equals 3. If we use a step size of 1/2, how many iterations are we going to need to do to estimate y of 3? That's right, Renaud. Very good. 4. Here's the first step. Step size is 1/2. So first step gets you to x equals 1.5. Second step gets you to x equals 2. Third step gets you to x equals 2.5. And the final step gets you to x equals 3. Okay. Okay, are there any questions on that? Okay, well, let's go look at the solution. So we're going to need 4 steps. So I wrote it out here for you. Here initially, x sub 0 is 1, y sub 0 equals 0. X sub 1 is 1.5, because if you take 1 and add 0.5, you get 1.5. Now the differential equation is y prime equals y minus 2x. So y minus 2x here is your big f of xy function. That's how the book denotes the right-hand side of the derivative, when the derivative equals the right-hand side, that's the big function f of xy. So on the first iteration, I substitute in x sub 0 and y sub 0 for x and y in my derivative. Well, x sub 0 is equal to, the function is y minus 2x. So y sub 0 is 0, and x sub 0 is 1. And so when my first iteration, y1 is equal to negative 1. And this means, what's that mean? This means that y of 1.5 is approximately equal to negative 1. Okay, based on this result here. But we're not interested in estimating the solution at x equals 1.5. We want to estimate the solution when x equals 3. When we know it's an estimate, right? So I have to keep iterating. I have to now do the second iteration, third iteration, fourth iteration. So on the next iteration, x2 equals 2, and then y2 equals y1 plus h times f of x1, y1. Well, x1 is, or I'm sorry, y1 is -1. We got that from the previous iteration. Okay, y1 equals -1. We got that from the previous iteration. Man, I can't circle that. I want to circle it without blocking it, you know. There we go. And x1 is 1.5. So you see, x2 is -3. So the nth iteration builds off of the iteration before it, as you can see. Well, after the fourth iteration, we get y4 equals -12.25. And so this means that y of 3 is approximately equal. I don't have enough room, do I? I'll have to put it down here. Hold on. Sometimes it's hard to control the stylus. I don't know why. Just got to get used to it, I guess. Now, I have a question for you. Is this correct, what I wrote here? Is this statement correct? When x equals 3, does the value of the solution, I mean, we don't know what the solution is or what it looks like, but when x equals 3, does the value of the solution equal -12.25?
No.
No. What do we need to change here in this statement, Samuel? I mean, we got -12.2.
In the y prime statement.
No. I'm saying when x equals 3, what's the value of the solution? This statement says the value of the solution to the differential equation when x equals 3 equals -12.25. And that's right, Maria. We need to say approximately. Very good. Very good. That's what I was looking for. Do you see that, Samuel? Do you see that? That's all I was.
Because we're giving estimates.
That's correct. Euler's
Got it.
method gives estimates. Are there any questions at all? Naturally, if the step size is very small, if we had a step size, let's say we had a step size of 1/2, but what if we had a step size of 0.25? How many iterations, if the step size were 1/4, how many iterations would we need to approximate y of 3? 8. That's right, Maria. And you know, that gets to be, since you're working these out, so you have to work them out by hand so you have a feel for the Euler's method. But naturally then, there can't be like, you know, I would think 8 iterations would be the most you would ever see, and it'll probably be less than that. But there are programs that can well, you know, I'm sure Desmos can do it if somehow probably, but you should be working them out by hand, this kind of thing, because you know on your third exam I'll want to see the work. Are there any questions? Any questions? Okay, I will stop the recording.